Thank you for organising it. It's a very pleasure to be here and be able to speak. Anything that would say, interrupt me and ask questions, but given that I have my advisor in the front row and my student in the back, I think it's interrupted with echoes. I think it's more prudent. Oh.
John Ross is your student.
I'm talking to kids. Okay, so I should say much of what I'm going to write is front work with Annie Sabru, a student of mine, who now, sadly from my perspective, but great from his perspective, is of being an accountant. And then another bunch of it will be joined with Morgan, who's now in Belfast, and Sundry. Okay, so let's try and start reasonably gently. What on earth do I mean by profinite space? What is profiniteness? Just in case not everyone's quite seen it. So, topological space is profinite if it is compact compact, countable, and totally disconnected. What does totally disconnected mean? It means that the connected components are sequence. Okay. So we've seen this kind of thing reasonably often. I mean, the Cantor set. What about for a group? For a group, this occurs exactly when G is isomorphic to the limit. It's G mod n. This is for n open normal inside G. Okay. Or to put it another way, a profinite group is an inverse filtered inverse limit of finite groups. Okay.
Is that definition for spaces equivalent to being an inverse limit of finite discrete spaces?
Absolutely.
All right.
You have to say filtered, but it's actually much more annoying to prove for spaces than for groups. For groups, it's easier. And just because if one hasn't seen it, it's worth remembering open in a profinite group is going to be the same thing as closed plus finite index. Could you make use of that fairly often? Okay, good. We care about profinite groups. Well, one of the standard examples the integers. Finite groups are in particular profinite. Power groups are fundamental groups. The monomer stabilizer Sn. We agree that these things occur, that we encounter them, we perhaps carry them. What about an example of profinite space? Okay. So, I mean, the Cantor set yes, but here's one that I particularly care about. So SG set subgroups of a profinite group V. Okay. When I say set of subgroups, of course mean set of closed subgroups. Okay. Well, do you want to put topology on this? And you say, well, I can just use the Hausdorff topology. But you could also say that X3 is the limit over the opening or suffix G. Well, that's G. Yeah. We don't know if we can take the same limit twice. We're going to write this a lot. It will come up all throughout. So I can obviously topologize this space by giving it a limit topology. That gives me a topology here. That's the same thing as the Hausdorff thing. So I think we can now say that I am a topologist, and there are people doing topology in reference to an earlier conversation. What does H map to? H maps to HM mod N. And similar maps give you the maps of the diagram. And of course, this has action G by conjugation on subgroups. Great. Let's draw a couple of examples of a space of subgroups. Let's look at the space of subgroups. Something. That's easy enough. So here is the trivial subgroup. Here is the whole thing. Here is P ZP. Here is P squared ZP. Here is P cubed ZP. And it converges. So easy enough. It's just one point application of the chapter numbers. Okay, what about this P cross Q? The P not equal to Q. Well, here. So this is E. This will be ZP plus E. This will be E plus ZQ. This is plus ZQ. So it's just the grid. Okay. Nice and easy. Right. One more. Chords are very nicely counterbalanced. Needs to be quite gentle. This would be plus 10. This is an L with an accent, not a T, it's an L with an accent. Y-N. Fortunately, Magdalene is not in the audience, so I'm going to pronounce it Pelchinski space. Okay. And you'd say, you've said that is the N, the Pelchinski space for what N? And the answer is, this is the Pelchinski space for all N greater than or equal to 2. It's the same for N equals 2, as N equals 3, and so on and so forth. So you really can get some quite complicated topological spaces occurring. And it's no surprise, of course, that one of them is named after a Polish mathematician. Good. So I want to study stable homotopy theory with respect to these profile groups. Let's pretend I'm giving some motivation, saying, oh, we care about spaces, and we care about cosmology theories, and so on and so forth. What I've done, we're just going to skip very fast and get to speaker. All agree that spectra is where we want to end that with. So, stable homotopy. Theory. I want to give like two constructions, or at least going to define one of the constructions to actually justify that what I'm doing is the right thing, or is the sensible thing. So, I'm going to have a theorem. This is from paper Belfast from 2008. And it says for G, profinite group, there is a model category of orthogonal G spectrum. And if you take the profinite group to be a finite group, you just get the usual category of orthogonal G spectra. And in case anyone's worried, I'm really doing any genuine things, of course. We take a complete universe for this profinite group, and one can worry a little bit about the universe, but it all works fine. And it is symmetric monoidal, low symmetric monoidal, stable. Of course, it is. It's G stable if one wants to define such a thing. It is finitely generated. It is all the things one could reasonably ask from any category of orthogonal G spectra. And you just follow the usual instruction of orthogonal spectra and just work a little bit harder in a couple of places to take care of the fact your group is profinite. But it's really not. Really not that much more complicated.
Does it make sure? Because a G plus cofinite.
No. In fact, let me actually speak to what are the GCW complexes. These are built from.
Hey, maybe before you say that, I mean, when you say genuine, what do you control the fixed points for? Just the all
Say that in a
closed,
second.
all closed or all closed and finite index?
All closed to finite index.
Okay.
Just following cells first, with equivalences later. That's what Right. So in particular, when you have an object G mod E, but it's not a GCW complex, it's not cofinite, and by and large, as far as I can tell, it's G mod E plus is just the same as a point. Anyway. We kind of want to only take G mod H plus for H open, so that our GCW complexes are in particular CW complexes. If we allow closed cells, I mean, I would have to think quite carefully as to what extent that it actually counts as a CW complex. I argue it's not. With equivalences are isomorphisms of homotopy groups. Let's start. Good. Right. So in particular, I want to be category G spectra, and I mean we can do all of this rationally again. Make a homotopy category of rational G spectra. Right. Text notes. Exactly. Rigidly generated. That's
Can I ask? Rigidly generated means like generated by dualizables, or?
correct. The dualizables and the compact and everything else are all the same. And so all of the things that I would normally want as a person from the model category world to know that I've got generators and they're compact and they're generalizable and everything else all occurs all at once in this compact rigidly generated case. Okay. Category. So, what about the actual homotopy theory itself? Well, I mean, we have quantic splitting for this case. We have molar isomorphism with the inclusion of an open subgroup H. There is some existence of Adams isomorphisms. That's a little more complicated. And it's a little unclear if we know sort of all of the cases that should exist. And I mean, Brown representability holds, so if you did really care about homology and cohomology theories, it's fine. We've got the same relation. And there's an equivariant version of the Freudenthal suspension theorem. So, you know, everything that you would reasonably want is there. Modulo having to say open in order to get Wertmuller, having to be just quite cautious about what happens. The Adams isomorphism.
Wait, can I ask, the Freudenthal suspension theorem for suspensions for what spheres?
Equivariant series.
Like representation spheres?
Yes.
Of, okay. Or is it just of G?
Of G.
Okay,
But I mean, finite dimensional representations of G.
okay.
And if G for a finite variable acts on a finite dimensional representation, it factors the refinite quotient.
Okay.
So I feel like the representations that you care about are really the representations of the G mod n for the varying n, put them all together.
So do you know if it's true at the kind of infinity categorical level that that this category is just the co-limit of the G mod U categories?
Spoilers.
You're spoiling things. You don't set the groundwork. Yes. Let's go. Right.
Yes.
So how do one actually calculate it? How do one actually calculate this stuff? Right. So here's this nice little proposition. Me and Danny. 2000. Right, so let's take H and K, open subgroups G, then I've got suspension spectra of these things. Because they're both open, their intersection is open. Because their intersection is open, there is an open normal subgroup inside them. So I can put U1 in here. And I can write this for any n, saying if n is inside H intersect K, I mean the obvious thing, maps of spectra. And if n isn't, I just ignore it. And then I take the colimit. And again, colimit over the canonical diagram. And what is this thing? This is, of course, just a nice perfect 2. G. And this fact, which I mean, is not so hard to prove, gives. I mean, this should be obvious, I think, for the people who know what they're doing, but that certainly wasn't me back in the day. Myself, Toby, and Scott. And where did we get this? 23. Category of G spectra is isomorphic as, I'm going to say infinity categories for the moment. And what should I take here? I'll take the colimit over the canonical diagram of G and N spectra. How do I get from here to here? I use inflation. So this diagram is using the inflation maps. But I could just as easily write this as the limit the Gmod and that spectra, now using fixed points to give you the maps in the diagram.
So here, when you write colimit, you mean this is the colimit in like PRL? Not
So
in CAP.
in PR,
Okay.
this is in, right?
And so that's the limit as computed in CAP, but that's not the colimit that's computed in CAP.
Good. Right. So I'm gonna. Right. And I mean, one way to make this colimit is to take the compact objects, take the super colimit in PRL compact and then incomplete at the end. But that's the same as just doing it here, I believe. Okay. So I think this is kind of cute in a way. I mean, you can make these things just naturally, they have good properties. And, you know, to me, this is a kind of reasonably rare case of when you've got an actual colimit or limit, and you've actually got like a model for it that pre-exists that you can actually work with. And I mean, the proof that this is true is just this, right? Which for me was quite satisfying when I realized it was that plus formalism, because I didn't really understand, like, how would one know, to give you a colimit, how would I know what a model for that colimit is? And one answer is you want something a bit like this. But it tells you that we're doing the right thing, right? I've taken the homotopy theory for all the Gmod ends, I've combined it all together, that's given me the homotopy theory for G spectra, right? And obviously, of course, the whole thing works rationally. In case you're anxious about, is this the same thing as the spectromatic functor approach of our very own log? Of course it is. Is this the same as the parameterized G spectra of Batman and Hoyers? Of course it is. This is the correct thing to do. Anything that is not going to give you that statement at the end is definitively the wrong thing to do. Okay.
To make that precise, you make like the subcategory of the orbit category on like Gmod open.
Yes.
Okay,
Yeah.
I understand.
Okay. So I said it didn't work with spaces, and I didn't want to work with cohomology theories. I wanted to work with spectra. That was, of course, a lie. I don't want to work with spectra at all. I want to work with algebra. Models or rational G spectrum.
Wait, can I ask a question about this whole everything else is wrong idea? I mean, I'm sympathetic to it, but you can't imagine a version of G spectra where I allow it to be meaningful to talk about the genuine G fixed points for G itself.
Yeah.
And that would be different from what you've done, right? I can't, like, if you give me a G spectra in this sense, I can't tell you what the G fixed points are, the honest G fixed points are.
I've no idea how to do that. I mean, it's like the forgetful functor as you would write it down in Faust's model from G spectra to spectra. I mean, that's not a writer job, because the lefter job would be giving you the free G spectrum, and they're not cofibrant.
Okay.
But when you write it in this limit thing, I mean, you can make all kinds of extra functors, and I can forget each of these down to spectra. And they're going to have lefter joints, and we can't quite work out what's going on. So there's some strange questions on what actual adjoints do you get for this case, and what if I wanted to do the G case. Or rather, the correct answer is, you know, this proper equivariant homotopy theory, right? So there you take, you compact your group, you look at, instead of quotients, you look at subgroups that are compactly, and you build the equivalences from those. And that's described as a lax colimit, right? So the dual thing of that should be a lax colimit, in this case, a lax limit.
Yeah.
So, yes, and that's how I would suggest on builds it.
Ah.
And so, I mean, is this framework good enough to support the kind of Devenant-Hopkins type thing where you take that fixed points of Morava E theory and the stabilizer group action?
I think the short answer is no. I mean, that's generally working in the non-genuine case and then taking homotopy fixed points to reintroduce it. So I don't think that fits into this framework.
I mean, this is precisely what you were just talking about, right?
Yes.
Like, because they're mostly concerned with finite subgroups.
Okay. So, I want to make an algebraic model for this. I want to do everything in algebra. It's easier, simpler to write down and all the rest. And let's start with the Burnside ring, right? So, definition. Burnside ring of algebraic finite G is the arithmetic ring of finite discrete G sets. And we do actually have to say discrete here. Just as an aside, X is discrete, so it's a finite G set. X is discrete with and only so overall we really continuous G actually. Right. If and only if factors on some orbit 2 over and over. So I could also just say finite sets, right? And then stick in that action, right? I think this is quite fun in that I remove having to worry about continuous things or put a topology on it, but just a straightforward algebraic statement, which is that the stabilizer of any point is an open subgroup. Okay. Here's a lemma Francis paper. I should give this a name. G. Burnside ring is the Burnside ring. Okay. Good. Well, I'm going to look at this rationally, because rationally you're going to get lots of impotence and they're going to be really rather. So, maybe Q of G, which is A of G tensor of rationals, which is SG Q or tensor Q, whatever you want to call it. How does this relate AQ of G mod N? It relates in exactly the way we've seen everything before. Just take the coordinate over the diagram. And that's quite rational, right? But it's true. Good.
Excuse me. So the previous the construction of G spectra, what the functionality in G? What's the functionality of G spectra in G? What homomorphism induce a restriction? You can restrict any continuous homomorphism of Profinite.
So, I mean, I can take fixed points for any open subgroup. I can restrict, anything for any open subgroup. But I think we can take a bit more of fixed points and still get equivalent adjunctions. I mean, in general.
So, for example, you had a quotient of G.
Yeah.
And you would try to do inflation. What type of quotients do you have? The trivial group will not be you cannot inflate. Okay.
I think it's something like H needs to be finite indexing, it's normalized, right? So you get slightly more than just all opens. Uh, Okay, so I want to understand this thing and get some idea of what the idempotency in it are. I mean, it's a perfectly good group, you've got a description and all the rest. But if I said, tell me an idempotent of this thing, you know, people might struggle to kind of get anything beyond 0 or 1. But we know what this thing is, right? And it's just the same thing as, so I'm going to keep carrying the code around, it's worthwhile. Of continuous function from the space of segments of SG mod G mod n into the rationals. Of course, the rationals is the discrete point, right? Or if you like, this thing, you've got a colimit, but then it's just a product over conjugated classes of subgroups of copies of Q. Okay. This is pretty handy, there's homomorphism. We kind of want to know, well, what's the equivalent up here going to be? So, I want to tie up this colimit. I mean, everyone's happy with the following, right? If I have some kind of mapping object, and I have...
We have said it's horizontal homomorphism is an isomorphism. Right?
Yeah. Right. I mean, this no. We're happy with this one, right? Any mathematician can do this. Well, with a little bit of magic, you can take a colimit inside a mapping object as well. At least in this case. That's G mod n, oh, G mod n, into the rationals, which is of course just the same thing as unit SG the horizontal map is the homomorphism, ghost homomorphism as usual.
You mean SG mod G or?
Thank you. So with just a little bit of magic, we can bring a colimit inside and turn it into a limit, and then we get this nice description. It's kind of the pattern that we're going to use a bit later, in that I take my general case, write it as the canonical colimit of the finite quotients, deal with that there, and then tidy it up at the end. Okay. So we know what's going on with the Burnside ring, and if you want to have it to talk at half an hour in, one thing you can do is you can say, right, well, I know what the space of subgroups of set P looks like, let's go calculate some idempotencies. That'll give you an exercise in case you're bored. Right. Yes, I'm going to get this bit as well. Let's draw the same picture but for G spectra. Now that we've got the pattern, the idea in our head, use G spectra rationally, and here is the limit of the diagram, then spectra, and yeah, we want to map into the limit. That's an isomorphism. What do we know about this? I mean, these are finite groups. So, replace this by limit open G of, right. What's the algebraic model for finite groups? We've got, okay.
Finite groups.
Modules of the rings of the file groups.
Yay! All together. WGH, where, I mean, just WGH is the normalizer of VFH of Hutchinson. Okay, good. Right. This is the symmetric monoidal equivalence. This here is the symmetric monoidal equivalence. So we've got an algebraic model, we can all stop with the talk stuff. But I kind of want some more detail on what this thing should be, right? I mean, like I genuinely claim that down here, telling you it's continuous functions from SG mod G to Q gave you more information than just saying it's the code. So I'd like to put something up in this column here. And that's going to be what we do for the rest of the talk, is work out what we should put up in this corner to give a nice description of what this category actually is. I mean, in terms of this actual bottom arrow,
Should we call him for those links?
you can read economy, yeah. They're the same. The co-limit is equivalent to the limit, right?
They're like in different
It's like the
categories for
theoretical
different diagrams, right? Wait. It's like that co-limit and limit, which are different diagrams and
Okay,
in different categories.
Yeah, but the isomorphic has
Yeah.
affinity categories, right?
Yeah.
And if I say limit here, then you know that this is monoidal off the bat, right? Whereas if you say co-limit in PRL compact, you have to work a little bit harder. I don't understand, so maybe explain it to me. I mean, yeah, we can say co-limit if you want.
Dave, before you go on,
Yeah.
this file group is the normalizer of H, is it the normalizer of H and G mod N? Is that different from the normalizer of H and G?
Yes, it should be. Thank you. Yeah, I mean,
How many G's?
I don't have to say how to my name. Okay. So, how are we going to actually answer what goes in that top right hand corner? And the type of way? The answer is going to be some category of equilibrium. So, Donald basically just because maybe it's been a while since we've seen it, I'm going to assume everyone knows what a sheaf is, but not necessarily that everyone knows what an equivariant sheaf is. So I'll let G equivariant sheaf of Q modules remember a topological space. G space X is map E to X. So E is going to be our G equivariant sheaf, and space E is G equivariant. E is a sheaf of Q modules. Let's just say P is a local homeomorphism, and then the stalks have the structure of Q modules, and the addition on these stalks extends to sections nearby it. So the usual sort of sheaf of Q modules that you prefer, any particular description that you like, and each. So I'm going to map G from pre-image of X to pre-image of G of X. This should be map. If you prefer to describe your equivariant sheaves in terms of cocycle conditions, that's fine. Like all the different versions are the same. I just like this because it's slightly easier to write down to a less expert audience. We know what a sheaf is, we know what an equivariant map is, and this is all that we need. Okay, great. So you can go work with these things, and you can make skyscraper sheaves, you can make constant sheaves. You can even play around with taking things like G maps from X to Y, taking pullbacks and push forwards of sheaves. You can even start changing G and get these kind of equivariant maps. You can even then change G and X at the same time and really make your life difficult on a person if you so wish, but you can do it all. And it's all the same and it's all fine. Okay? And that's an action of stabilizing of X. Okay, good. So here's a theorem. This is from Danny's thesis, all the way back in the before times. You can find through. I haven't told you what Mackey functors are. I invite you to imagine what a rational Mackey functor is. In particular, it takes values m, the G mod h to h open. I don't need to tell you what this is. Standing has an exact equivalence with this category of while G sheaves over Q and SG the space of subgroups. So I told you what G sheaves are, I told you what SG is. All I need to tell you is what this while condition is. And all this amounts to is that the stalk over H, H being a point here, H a closed subgroup, PH is fixed. So rather than having an action of the stabilizer of H, which is the normalizer, has an action of okay. The really fun part about this is I've been saying open all the way through, but now we get to sheaves and I need the set of closed subgroups, the space of closed subgroups, in order to get all of the stalks. And, well, let me put it on this one. As a consequence of that result, because I mean, you know, we know that the homotopy theory is going to be concentrated in degree 0, so we're going to be able to use Schrader-Shipley's Morita theory in order to get across to rational Mackey functors, right, or spectral Mackey functors or whatever. So as long as I say chain complex, the thing to look here is chain complexes while Q over XG. And we have an equivalence here. So, take the limit of a product category, what do you get? You get a sheaf category, right? But I kind of want to put something in the middle here to kind of show a bit more as to, well, yes, you can do this via the Morita theory, but you lose the monoidal structure. Right, I mean, this was tensor, this was a monoidal equivalence, this was a monoidal equivalence. So is this a monoidal equivalence? Can I do something here? Well, you take, not this one. You take this category. I mean, yes, you've got different group actions in different places, but I mean, this whole thing is just chain complexes of while. What is this category here? The product category. Chain complexes while in whatever sheaves. rationally over xg mod n. Right, so you ignore the limit, you ignore the chain, you just take the product, and that's just exactly this category, right? Because the space is discrete, so all you care about is the stalks, what's happening in the stalks, you get an action of the bar group, which is why we had that assumption there. So, again, ignoring the limit, the fact that these two things are equal, it's obvious. Right? You know, I said before, with a little bit of magic, you could bring that co-limit inside. Well, with quite a lot of magic, I mean, you can get an equivalence of one category, right? I don't say infinity. Ignore the chain complex bit, that's not necessary. But you can bring this limit inside and change this G mod n to a G, and bring it inside and change this G mod n into a G. Well, it's that in tensor equivalence. This is an equality, so that the 3b's and 23 equivalence is, I mean, prove it by going around. It's exactly the same thing as lots of group did. Okay.
But the downward arrow, it sort of forgets what's happening on the closed but not open subgroups. So the one you're saying is an isomorphism. It looks like it's forgetting about non-open. I mean, the upstairs, the SG had the closed subgroups, the non-open closed subgroups.
Yeah.
As points as well.
Yeah. But down here, I approximate this closed subgroup H by the sequence of closed subgroups H n mod n. Right? And it's
No, I agree with going the other way. If everything else is an isomorphism, then this one has to be as well. But it is, there is something, it looks like you're forgetting something. Right? I'm just trying to,
yeah.
I'm just
I mean,
trying to
I
understand
think
the
it's,
map that's supposed to be an isomorphism.
The one that
It's kind of a good
lots
question.
of magic.
right? One sort of says, well, can you sort of put things at the stalks of closed subgroups? And the answer is you can. In fact, you have to. So you can get this kind of behavior where a skyscraper stalk, which is only non-trivial for a closed subgroup and is trivial everywhere else. Right? And in some ways, like how to see that those things exist here, I mean, that's coming from this, the idempotence, right? Like I don't have an idempotent that just picks out a closed subgroup, unless that closed subgroup is isolated. But I've got a virtual idempotent that will do so. I've got a sequence of idempotents, right, which will converge to just that point. I just take a neighborhood basis. And so these kind of virtual idempotents do allow me to pick things in. I think I've answered your question. But yeah, I mean, I do enjoy, like, everything on this side is open, only things here are open, but when we get to here, we see that the closed subgroup really did matter.
Can I ask for my own understanding? If you start at lim like G mod n spec, like rational G mod n spectra, and you go up and to the right, and then evaluate at a stalk which is closed but not open. It is just like you somehow take like a limit of all of the like
Exactly.
Okay. Okay.
I mean, really what I want to say is that X here is sent to the thing which stalk at H is, except I'm not entirely sure that I can define the H geometric fixed points of X. Except, I mean, I want to say something like the colimit over H n mod n, something like X. Maybe I should say something like this. But we're not entirely convinced that these formulas make sense either. We don't seem to try to think about it, and very much unclear. 4 minutes left. So, talk about sheaves.
Yeah, 10 if you want.
I now want to say something about tensor-triangulated geometry, which is a deep risk considering the audience and my level of understanding of tensor-triangulated geometry. Let's see how far I can get with the excuse Toby wrote that one. So, right. So let's go with this. I take spec of little stick. I'm told that I need the compact here for this to make sense. Is of course just the limit over n over normally g spec g mod n. So we understand spec of this exactly as much as we understand spec of G spectrum for Finite G, which, you know, it's a reasonable amount. I mean, I should say blue shift, and I will not say anymore. But if G's abelian, then we know kind of a lot. But if we do the same thing rationally, well, I mean, it is this thing rationally, so I should just write, of which we've already seen examples. Good. So we know what this thing is, right? And Q is stratified if only if S G mod Q. I would say scattered, but I mean, I think countable is more direct and easier to understand. So that the actual stratification of this thing as a TT category is dependent upon the actual topology of this space. Which means to me, it kind of gives this nice example. Here's a class of things which are stratified, here's a class of things just as natural, and they're not stratified because we picked SG mod G to be normal.
What do you mean by stratified?
What do I mean by stratified? A nice morphism between thick localizing ideals and the subsets of space. Okay. What do I mean by stratified?
Yeah, then you get a classification of the localizing ideals in terms of the subsets of the spectrum.
Ah, okay. Ah, I see.
It's a property that the category can have or not.
Right. I see.
So if G's abelian, if G mod G is countable, if and only if G is CP1, CPK, United States. Yes. So getting the abelian case is pretty easy. The non-abelian case, good luck. So that G is SLN ZP countable, or SG mod G countable if and only if n. So if n is 3, we're out of luck. N is 2, then you're in business. And then talked a lot about stalks, and now stalk that page in the T sense, which I take to mean those things in the homotopy category whose support in terms of spec is just concentrated over the single point H. Let's say E spectra U H is derive a category of the H modules. I have to put the delta up here to mean discrete. So that the stalk in the TT sense is really the actual stalk of the category of sheaves. You take the stalk at H, you get WH modules. Of course, you have to say discrete WH modules. Because with the TT case, you get the derived category. So, stalks are stalks, is what we say to that theorem. And
Thank you very much. Wonderful. Questions?
So, so when it's not countable, so given what you just said at the end, so the issue is the local to global principle, is that what fails?
yes,
Yeah.
because the other one is automatic in this case. You can ask me why.
See, you mentioned at the beginning that you were going to be telling us a lot about ZP cross ZP. Well, is that not what, did I misperceive that? I mean, do you have anything interesting to say about ZP cross ZP in terms of the spec?
Well, I mean, that's why you're not countable.
Yeah, but do you have anything interesting to say anyway?
It's a thing called the counter-Mendixon process.
Mm-hmm.
You take a Profinite space, you throw away all the isolated points, you get a new space. That's X1. You throw away all the isolated points again, you get a new space. You keep going, and then you can do this transfinitely if you so wish, right? If SG is scattered of finite rank, the homological dimension, or if you like, the injected dimension of HG's rational over SG is counter-Dixon rank -1, where, so I throw away the isolated points at each stage. So scattered and finite rank means after a finite number of attempts at this, I end up with the empty set.
Mhm.
Take that number -1, that gives you the homological dimension of these things. Okay? And I don't know how one calculates the homological
Does it
dimension.
make a difference? Does it make a difference whether you have the vial condition or not?
Not at all. Thank you. Yeah, it's the same answer for the vial case. I mean, we're just doing the Godemont resolution sheaves, and you do the Godemont resolution on a profinite space. What are you getting rid of? You're getting rid of the isolated points at each time.
Mhm.
Because if it's not isolated, you're going to get non-trivial serrations. So it's a lovely observation, but it's just that fact. Right. So what happens if you take ZP cross ZP? Start with that. There are some isolated points. You throw those away. You get a new space called H. You throw away the isolated points of H, and you get back something homomorphic to H. And it's this thing called the perfect hull. I think technically it's that that's the Belfast space rather than ZP cross the subgroups plus the subgroups of ZP cross ZP.
Okay.
And I mean, I can't tell you anything about a Polish space other than people have studied it and it's difficult.
So is the injective dimension infinite otherwise, is that?
Yeah. Well, I mean, if it's scattered in an infinite rank, then yes. You could be a finite rank and have a non-trivial perfect hull. We think that's infinite, but we never quite got around to proving it. Whether that tells you what you would want about the Adams spectral sequence is another question. But certainly in the scattered finite rank case, it does.
What's the answer to my question?
That it collapses at the counter-Dixon rank -1 stage.
But even when it doesn't collapse, it's still convergent. Addition.
Don't know.
What does scattered mean? I'm sorry.
So
Maybe you already told us.
you apply the Cannon-Dixon process, you keep going, you end up with this thing that keeps repeating. That's called the perfect hull.
Mhm.
Everything that's not in the perfect hull is the scattered hull. You are scattered if the perfect hull is empty.
Oh, I see.
Among the profinite groups, you have the absolute Galois groups. Do they play a special role in this stuff? Is there special behavior that you observe in there?
It'd be nice if they did.
Some of them are going to be quite scary, though. I mean, in characteristic P, if you look at the absolute Galois group of FP round brackets T, that's not even of, it's topologically infinitely generated. So it's going to be in characteristic P at least, I would expect these things to be really nasty groups. I don't know, maybe if we thought about like GT hat or something like that, maybe it would be a little more down to earth. The estimate for the absolute Galois group of Q is given to you by this profinite growth in the Untitled group, and I guess you could play with that example and see what happens, because that's kind of concrete.
Yeah, so if we look at the rank 1 subgroups of ZP squared, so in particular you seem to be saying that that's not a Cantor space.
Yes.
Is it clear that it's not a Cantor space?
It certainly isn't to me.
Okay.
Right. Let's meet again, or just remind you that there's another talk at 15:30, but we have a break. Thank Liv again. Thanks.